All right, we're analyzing a different type of data now. Okay, last couple of days we've looked at sample means. Okay, now we're asking a completely different kind of question. What percentage of these 1,800 students are girls? So when I look in here and I take these out, I'm not seeing a number anymore. That's called quantitative data. When I look in here, what am I seeing? Just boys and girls. That's the only thing you get off this piece of paper. Binomial. This is just a binomial problem again. It's just going to be males and females. That's all I'm going to see. These aren't numbers. This is categorical. And there's only two categories, two things to choose from. And this is what I'm trying to figure out. What is the population probability of being a girl? I think this was about 47, 48%. But we don't know that going into it. That's what we're trying to figure out. Now these are just letters, so there is no spread and there is no shape. These are just yes and no. Okay? Then here's what you did. You reached in here and you grabbed 10 of them and you found your sample girls proportion. That's what you're going on television with. That's what you're going to predict for the entire school. Okay, I asked someone third period, I said, what did you get? That person happened to get 0.5. That's what you're going on television with. But here is what we're studying. This thing called the sampling distribution, which is every possible p-hat. Remember a sample proportion, we call that p-hat, that you could get. So let's go through this class. Put some of your class up here. So Madison, what did you get? 0.5. 0.6. 0.4. 0.3.
Okay, girls, 0.7. 0.5. 0.6.
0.5.
0.5. 0.4.
0.7.
0.5. 0.4. 0.3.
0.4. That's where we at. Okay, that's where we're at. All right, take a look at these. Okay, this is an example of where your 1 is. This is what we're studying. We would love all of these to be really close to the right answer, but look at the variability. Someone got 1 girl out of 10. 10%. They're going on television saying that Elk Grove High School is 10% girls, based on their analysis. We have some pretty big sampling variability here. Why do you think that's so? Why do you think the sampling variability is so big? No idea. Yes, yes you did. Small sample size. Remember, it could be very random in the short run? Absolutely. What if we'd have taken a sample size of 50 people? You'd have drawn 50 names out of there. Do you think you're going to get a 10%? No, it's going to be much closer. These are going to get more bunched up around the right answer, and that's good. Okay, let's analyze this. Let's describe all of these p-hats now. First thing, p-hat is also an unbiased statistic. What does that mean? That means if we kept going and we got every possible p-hat there was, in this problem it's 1,800 choose 10. That's how many different combinations of 10 you could pick out of there. And then you went and found the p-hat for those 10. And you got them all up here. If you took the mean of all of those p-hats, it would be equal to the population proportion, right on the money. That's a good thing. At least I know the right answer is in the middle of all these. That doesn't help this person. I mean, they're going on television with a bad one, but at least the right answer is in the middle of all the ones that you could possibly get. We also have a formula that calculates how spread out these are. This is the formula that calculates how spread out these are, typically how different they are from the true proportion. And it's this, the square root of p times 1 minus p divided by n. Didn't say this last time. These two formulas are on your formula sheets. Go find them. They're on page 5. It's the top box on page 5. Now this should kind of make sense to you now. I'm looking at that top box and I say, hey, what statistic are you dealing with? Oh, I'm dealing with X bars. So if my statistic is a bunch of X bars, you want to know how spread out they are? Square root of the population, standard deviation divided by square root of n. Oh, we're not talking about sample means. Is your statistic p-hats, where you're finding out the percentage of something from your sample? Okay, if that is your statistic and that's your sampling distribution that you're looking at, that's the formula for how variable all these p-hats are going to be. Okay? Not formulas you have to memorize. Okay? But they're there.
So will categorical information always be the sample proportion, and then...
That's the key, okay? Look at what the original data was. Was the original data categorical? And in fact, there's only going to be two categories. It's going to be yes or no, just like binomial. If that's the original data that you're working with, yes, then we're going to be dealing with p-hats. If the original data was numbers, quantitative, then you're going to be dealing with X bars. Why this is so confusing and hard, you did a problem last night that was in percentages. It was like how much your stock went up or down. But even though it was in percentages, you were doing X bars because the original numbers were in percentages, and those were real numbers, not yes and no. Okay, so that's one of the trickiest parts of this. Would you have a follow-up?
No.
Okay. All right. Yeah.
So does that mean that this is going to apply to things that have a yes or no, which means they have a sample probability?
Well, now wait a minute. These are yes or no, but does that mean that there's 50% girls on campus for sure?
Oh, no, I meant the sample.
No. This was just one person's.
Oh.
I asked, the first person I asked in third period, I said, what's your probability for girls?
Okay.
And that person said 0.5. So remember, that's just the one, but all of you have your one up here, right? That's what you're going on television with.
But it's yes or no.
Well, here it's the percent. So you had to go do some calculation here, right? You had to do 5 over 10. Okay, so these are real numbers based on how you got your p-hat. The original, when I look in there, it's either each one is either a boy or a girl. Okay. All right, and then finally, what shape will all these p-hats come? Now, this is just a binomial problem. Fixed number trials, taking 10, it's all the same. Notice the check that we're doing here. Remember last chapter when we were checking to see if the binomial distribution would come out normal, np times n1 minus p must both be greater than 10? That's the check we do here to see if all of these p-hats will take on a normal shape. Okay? Notice there's no central limit theorems over here. There's no population distribution, blah, blah, blah over here. There is no population distribution. Just a bunch of yeses and nos. Okay? So that's the only check you do if it's a proportion problem. Okay, let's do one together. Now, when you guys read these problems, I want you to equate them to what you've been doing. When you read these numbers, you'll be like, oh, where on that board are these numbers? So we're going to work the problem together. It's on page 507. So open up to 507 and look at the example that's in the book. And like I said, when we go through each one of these measurements that they give you, you should be on that back wall saying, what is that? What is that? Reading the problem on 507. All right, here we go. A polling organization asks a simple random sample of 1,500 college students. Stop. 1,500. What is that? Back here, and what you just did, what is going to be the 1,500? You got all kinds of letters, all kinds of stuff. What does that 1,500 represent? No! It's the sample size. You just took out 10, right? They're taking out 1,500. So what letter would it be? Little n. It's the sample size. You guys took out 10, right?
I got my blue pen.
Okay, so it's little n. So that's what you need to do when you go through these problems. Say, okay, what is that? All right, the next thing. And ask them whether they applied to another college as well. In fact, 35% of all first-year students applied to colleges other than the one that they're in. 0.35. What is that up on the wall? What is the 0.35? What? Now, come on now. Now! You only had 3 options. You picked the wrong 2. Now, that's your third choice. What was that 0.35? It said 35% of all first-year students. And Reese said it's... Really? No. Let me ask you again. Did it say that 35% of the sample?
No.
Or did it say 35% of everything? It'd be like saying 35% of the entire bucket.
It's a P.
So what is it? Big P. It's the population parameter. It's not the p-hat. They didn't take the 1,500 and have 800 of them and find the p-hat to find the sample proportion. They're giving you the final answer. Guys, this is the same problem as the elections. Okay, on election day, everybody goes and votes. Before the election, people go out and take samples and they go on television with their guests, and it's only on election day that we find out the right answer. In this particular problem, they're telling you what this is. Now, the reason why they're doing this is we have to use it in our formulas over here. But understand, 35%, big P, the capital P is 30.35. Yeah.
Are we going to learn how to be able to get the population information?
Okay, didn't go very well. All right, what is the probability that a random sample of 1,500 students will get a result within 2 percentage points of the right answer? So all of these p-hats in this problem come from a sample size of 1,500. What this is asking for is what percentage of these are really, really close to the right answer. This is how they do the election thing. If they take, and now you guys learned that elections usually ask about 2,000 people, right? We're going to learn more about that later. But if you ask 1,500 people, what we're figuring out right now is, hey, what kind of, I don't want, mine's only one of these, but what's my chances that my guess is going to be super close? That's what we're saying. What percentage of these are within 2 percentage points of the right answer? So now they're asking you to analyze all the p-hats, the numbers in the sampling distribution. All right, so let's get this started. The first thing that you're going to do is our assumptions again. Because anytime we do a problem that's dealing with the sampling distribution, we must do our assumptions. Assumption number 1, I'm going to let you write SRS. We're asking a question. Did they take a good simple random sample? Or is this, I don't know, did they go to some rich people high school where they can apply to any rich school in the world and they're going to apply to a bunch? That wouldn't be a good sample. Okay, did they take a nice random sample of 1,500 students of all the students out there? And all the colleges, did they take a good simple random sample? And they did. They said it was stated. Okay. Yeah.
How do we know people aren't lying when they just say that?
Yeah. I know. Trust them. Although there's some problems that you're going to do, and they'll use the SRS, but then they'll explain how they did it and it wasn't very good. So you got to be able to pick that up. You got to read carefully. All right. Now notice we're checking out a different formula here. This is the formula for how spread out the p-hats are. So we're asking ourselves, is this the right formula? There's a different one if you take too big of a sample size compared to the population size. Same check. Okay, we want to make sure our sample size is less than 10% of the population size. Is 1,500 less than 10% of all first-year college students? Yes. That's a pretty safe assumption. And then the big guy here, will the sampling distribution of all the possible p-hats, those blue guys back there, if I create a graph of them, okay, would that graph be normal? All right, notice what we're checking out here. I don't see any central limit theorems or any crazy stuff like that, right? This, when we're dealing with proportions, sample proportions, this is the test that we do to determine whether the sampling distribution of all the p-hats is normal. All right, what is n in this problem? 1,500. What is p? 0.35. I think that is 525. Then we got to do 1,500 times 1 minus 0.35, or 0.65, and that's 975. And you've got to show, you have to check. Those are both greater or equal to 10. We do have a normal sampling distribution of all the possible p-hats. So now, based on number 3 here, I can draw this. Okay, what do I put in the middle?
Your P, which is 0.35.
0.35. Why? Because I know that the mean of all the p-hats is equal to the population parameter. And they told me in this problem that the population parameter was 35%. Now they said, hey, what's the probability that I get a p-hat within 2 percentage points? So I go out here and I go out here. So what's 2 percentage points this way? 0.37. 2 percentage points this way is 0.33. And that's what I'm looking for. What percent of all those p-hats will be within 2 percentage points of the 35%? All right, got a little bit of a different z-score formula going now. So what is my z-score formula going to look like now?
Square root of
Z-score. I want to find out how many standard deviations these are away.
what would be the p-hat?
Good. P-hat. Correct. We're in the world. I want to know what percentage of the p-hats minus?
Mean. Oh no.
It's big P, right? The population parameter. How many standard deviations is this away? Big P. And now over...
So square root of p times 1 minus p over n.
Very good. Okay. That's our new... We want to try to figure out how many standard deviations away this 2 percentage points is. All right, let's plug in the numbers. So in this problem, it's going to be... Point...
Oh,
Plugging in the numbers. 0.37 minus 0.35, that's 2 percentage points, over square root of 0.35, correct, that was the population parameter, times 0.65 over 1,500. Plug that into your calculator. Let's see if everyone can get these parentheses right and all that stuff. Let's see if you can see how many standard deviations away those 2 percentage points are. Number out there? What do you got?
1.62.
I think that's 1.6, yeah. 1.62, 1.63, right in there. Okay, remember that goes on our picture. So this in standardized scores, those 2 percentage points is actually 1.62 standard deviations away. This is symmetrical, so this would be negative 1.62. Show that math if you want to. Now, let's go find that percentage. Remember, you have to subtract the 2 proportions you get from your tables. Find Find the probability of the percentile for one of them, find the percentile of the other one, subtract those two numbers to find what's in the middle. Did I get one for me yet? 0.8971. That's about right. Very close. All right, I need you all just to put down your pencils just for a second. Step back and think about this for a second. And this is just how it works for the elections. Elections, there's millions and millions and millions of people that are going to vote. Yet if we only take a sample size of 1,500, we've got a heck of a chance to get a p-hat that's within 2 percentage points of what it's going to end up like on election day. Doesn't get any bigger than this, guys. This is it. This is as good as it gets right here. Only 1,500. I asked you guys, you got an election, 50 million people are voting. How many do you want to ask so you can be pretty sure you got close to the right answer? I want to ask 25 million people. No! If you just ask 1,500, you got like a 90% chance that your one little p-hat is going to be within 2 percentage points of whatever that right answer is on election day. We're going to study this a lot further next chapter, but that's the big picture. That's why we study all these p-hats. Because we know our answer's got a really good chance now of being really close to the right answer. Okay? Okay, any questions?